In the last video, we derived the relationships for the simple harmonic oscillator. And where I want to go in this video is mostly to be exploring applications. But first, we need to take a look at first the result that we got. One way that we can recast the result that we got in the previous video series is to write that the acceleration is equal to minus 2 pi f squared times x, where x is the displacement from equilibrium. And now the thing is that although we did this result for a very specific thing, we looked at the mass on the end of a spring, and from that we were able to deduce the frequency of that it's simply harmonically oscillated to begin with and the frequency of its oscillation. The beauty of math is that the result is true regardless of the situation, as long as the variables have the same kind of relationship to each other. So as long as the thing on the left-hand side of the equal sign, we remember with acceleration, it's the time rate of change of velocity, and that is the time rate of change of position. If we can find a similar relationship with another pair of variables that are related this way, that system is also a simple harmonic oscillator. For instance, we could have this be angular variables. So for instance, if we find a relationship where we can write the angular acceleration is equal to minus something times theta, the something will be the 2 pi f squared of a simple harmonic oscillator, and this system will somehow be oscillating harmonically. And in fact, this shows up in even more systems than this. For instance, we could replace these variables with equivalent variables for electric charge and discover that there are certain electric circuits that act like simple harmonic oscillators. And so this is an important pattern to recognize in physics. If you see something that is the time rate of change of something, which in turn is the time rate of change of something, so the acceleration is the time rate of change of the time rate of change of position. If you ever see that time rate of change of a time rate of change of something on the left side of the equal sign, you have a minus sign, and then you just have the thing on the right side. Whatever the stuff is in between, that is going to be 2 pi f squared, and the system you have is some sort of simple harmonic oscillator. So although we did this very specifically looking at a horizontal, in fact, mass on a spring, we didn't even consider the vertical case yet. So although we only did this for a horizontal mass on a spring, as long as the variable on the left-hand side of the equation and the right-hand side of the equation has the same kind of interrelationship as acceleration and position do, if you can write whatever you're writing can be massaged into this sort of a situation, you found yourself a simple harmonic oscillator, and you can just stop right there because you know the answer, and you can identify the frequency. So we will be doing a bunch of examples of that in a lot of different situations. So the first of these I want to take a look at is the vertical oscillator. After all, it seems very reasonable to say, hey, when I hang a mass on a spring, so here, let me just kind of draw 3 springs here. First, I'm going to draw a spring that doesn't have anything on it, so I'll just draw a little dashed box there. And then we could imagine just plain hanging a mass on the spring. So this is in equilibrium. Well, already notice here that the equilibrium position of the system is displaced from the equilibrium position of the spring. The system just naturally wants to hang out at a point where the stretch is big enough that the force of the spring pulling up on it exactly counterbalances the force of gravity pulling down on it. But since the force of the spring is proportional to the stretch, there has to be some stretch. So as a result, we've shifted our equilibrium position a bit. Does this matter for our oscillator? Well, let's go and take a look. So let's just note this this shift in the equilibrium position. Let's call that capital X. And then let's say we do go ahead and we give our mass a pull. So now we're oscillating here. And let's say at the moment it happens to be a little further down. Let's call this offset from the new equilibrium position where it would just hang all by itself with gravity. Let's call that little x. I know that might seem a little confusing because normally we write little x as the stretch of the spring, but we'll be very careful here when we do this. So let's go ahead and write a draw a free body diagram for this situation right here. Well, right here, since the spring is stretched beyond the equilibrium position, the force of the spring is greater than the force of gravity pulling down on it. So we can go ahead and write Newton's second law for this. So let's go ahead and let's make down positive. I think that's going to make the most sense here. So making down positive, we can go ahead and write Newton's second law for the situation and say, well, we've got the force of gravity acting down. We have the force of the spring pulling back up, so minus Fs. That equals ma, and I'll let the sign of the acceleration sort itself out through the math. All right, well, let's substitute in for what these things are. So we'll have mg minus k. Let's see here. We're going to have our stretch being big X plus little x. So remember, the force of the spring is the spring constant times the stretch. We have to still measure it from the unstretched position. So this extra bit here, that's going to be x plus, big X plus little x. All right. And that has to equal ma. But now let's go and revisit the equilibrium situation for just a moment. So looking here, at this situation, I could just as easily drawn a free body diagram there. And here, the force of gravity and the force of the spring would be equal. So here would be right Fg minus Fs equals ma. Let's say a to 0. And then this would give me mg minus k. And here the stretch is just this big X. So that equals 0. Alrighty. So what have we got? What we can do is we can solve for this big X. So this would be equal to mg over k. And let's stick that in for there, now that we've figured out how much it's stretched by. So now we'll have mg minus k times mg over k plus little x equals ma. Let's distribute the terms out. So we have an mg minus, okay, now this first term is going to be minus k times mg over k. Hey, that's just mg. Let's be explicit, right? K mg over k and cancel. And then this term here, minus k times plus x, will just be minus kx equals ma. But look at this, you've got an mg minus an mg. Those two terms cancel. And so now we can go ahead and rewrite this as a equals minus k over m times x, and go, wait. We've seen this before. We know whenever I can write an acceleration-like thingy and a position-like thingy, if I can equate it to something with a minus sign and some stuff, then that means the stuff is equal to 2 pi f squared. So what we get is the exact same result as before. We get that 2 pi f squared is equal to k over m. So we can solve for the frequency. 2 pi f squared is equal to k over m. So taking square root of both sides, 2 pi f is equal to root k over m. And we get the frequency is 1 over 2 pi root k over m. So it turns out that from an oscillation perspective, what we are doing is we are still executing simple harmonic motion with the exact same frequency we had in the horizontal case we looked at in the previous video. The only difference is we shifted the equilibrium position. So instead of it being the equilibrium position of just the spring all by itself, it's now where the object sits in equilibrium under the influence of gravity. So it oscillates around this point here. This is my new center of equilibrium here. It oscillates about this height right here instead of this height here, but still does it at exactly the same frequency as before. Okay. The next example is going to seem a little unmotivated. It is an actual device that does actually get used in certain kinds of clocks, but I'm mostly going to be using this to lead into the pendulum. So in fact, the device gets called a torsion pendulum. So what a torsion pendulum typically looks like is you'll usually have some sort of a rod, like so. And then you'll hang a thin wire onto the rod. And then have some sort of an object. In this example, I'm just thinking of a disc or something. But if you've ever seen, there's these decorative clocks where there's usually like a collection of 3 or 4 weights hanging on a wire, and those weights spin back and forth, and that's how the device is keeping time. That's this device. The only difference is instead of it being a disc, it's that collection of 3 or 4 weights. Similar devices are sometimes used in watchmaking and stuff like that for timekeeping. And the idea goes like this. If you twist, so this disc, this disc has a moment of inertia I. If you give it a twist, what will happen is you will get a torque being exerted by the wire. The wire will get twisted and it wants to untwist. So say this is my reference mark right here. We'll make that angle theta. If I pull it back to some angle capital theta, yeah, that's what capital theta looks like. If we go and use our special paper from before, basically draw an O and stick kind of like a little H in it, that's a capital theta. So we go and pull it back, let's say to plus capital theta. I'll just go ahead and mark in a minus capital theta for some symmetry here. The wire itself will exert a restoring torque that's proportional to how much the angle that you're currently twisted by. So if the angle you're currently twisted by is just lowercase theta, it will exert a restoring torque proportional to the twist. So this letter here is not a K. It is a lowercase Greek kappa. There are a couple of ways to draw it. I usually go with the way that puts a little flaggy on it. But if you just write a half height sort of funky K thing like that, that's fine too. All right, so it's called, and this is called the torsion constant. It works just like a, works just like a spring constant. It's just telling you what the torque, what the restoring torque will be. In this case here, the restoring torque is indeed proportional to the angle you've been twisted through. Okay, so let's just start and see where that takes us. So for instance, we can say the torque is equal to minus kappa theta. All right. And we know that by Newton's second law applied to rotations, the torque is always equal to I alpha. So we can rewrite this as alpha equals minus kappa over I times theta. Now, it might not look like it, but it turns out you can say, hey, wait a minute, this is a simple harmonic oscillator. And this is because, remember, the angular acceleration is the time rate of change of angular velocity, and angular velocity is the time rate of change of angular position. So the angular acceleration here has the exact same mathematical relationship with theta as A did with X when we were looking at masses on a spring. So then what we realize is that this thing twists back and forth in a simple harmonic motion kind of way. It'll twist out to some maximum amplitude plus theta, and then go to the other turning point minus theta. It'll go at the fastest when it's at its relaxed position back and forth. It does all the same things, it's just that it's twisting back and forth. But again, we can play the same game here and realize that whenever we've got an acceleration-like thingy here, and a position-like thingy here with a minus sign there, that means that whatever you got here, that's 2 pi f squared. And so again, you can solve for the frequency of oscillation. We can say that 2 pi f squared is equal to kappa over I. Take the square root of both sides. 2 pi f equals root kappa over I. And f equals 1 over 2 pi root. Oops, there we go. Root kappa over I. Cool. So like I said, I'm not really making a big deal of this, but I was using it more as a lead-in to thinking about the physical pendulum, which is something a little more practical. So, as an example here, let's say you've got yourself some sort of shmoo-shaped object here. Oops. So if you get yourself some sort of shmoo-shaped object here, something like that, let's say there's your axis of rotation right there. And let's say the center of gravity is located here somewhere. So that's the CG. So if we go ahead and draw an extended free body diagram for our shmoo, we'll see that there will be a force of gravity down, and there will be a matching normal force up being applied at the axis. It's also just following typical physics convention, even though it's not a height, almost every book will call this distance here h. So I'm just following that convention. So we can analyze the torque here. So remember, to get a torque, we go ahead and find ourselves the line of action of the force. So here's my line of action here. This distance right here, from here to here, that is the lever arm for my for my force due to force of gravity. And that lever arm will be equal to h. And so let's go ahead and mark off an angle here. If this is theta, actually let me maybe do it like this just to make it a little easier to see. So let's say this angle here is theta. Then my r perpendicular here will be equal to h sine theta, because just extend that back. What we're looking at right here is this piece right there. This is my theta. That's the opposite. H is my hypotenuse. Okay. So with that, we can write that the, oops, sorry, let me dimension my theta here. We can write that the torque is equal to minus the force of gravity times the lever arm, and the lever arm is h sine theta. And why the minus sign? Well, again, it's the same deal. It's because it's a restoring torque. If I twist this clockwise, we can see that the force of gravity will be, if I pull this off to the clockwise side, the force of gravity will be trying to pull it down counterclockwise and vice versa. All right, well, we can put in what the force of gravity is. So we get that the torque is minus mgh sine theta. And again, we can apply Newton's second law for rotations. I alpha is minus mgh sine theta. And then we can try to get into our canonical form, but we're not going to be completely successful. We are going to get minus mgh over I sine theta. So close. But the problem is I needed this to be an alpha here and that to be a theta there. So in general, so this is not a simple harmonic oscillator. But physicists don't leave well enough alone here. It is a general rule of thumb that any sort of restoring force or restoring torque will look like a simple harmonic oscillator if the angles or the displacements are small enough. So kind of taking that clue. You might want to just, for funsies here, if you have your calculator available, or if you don't, you feel free to pause the video and find it. Put your calculator into radians mode. And then once you've done that, go ahead and punch in 0.1 radians. Here, let's actually just, oops, my bad. Let's actually just do that. Oh, I know. There we go. So we can put in 0.1. Now let's take the sine of 0.1 radians. 0.0998. That's not too different from 0.1. All right, let's try 0.2 radians. 0.198. Yeah, that isn't too different. Let's try 0.3 radians. 0.295. Okay, there now we're starting to get to where we're maybe about 0.2% off. Not quite. So out to 0.3 radians, that's about 20 degrees. It seems like the sine of the angle is equal to the angle as long as you're working in radians. If you push it too far, like say you try to take the sine of a radian, that doesn't work out so good for you. Now you're off by 16%, and that isn't going to cut it for what we're doing. But if we just go ahead and pinky swear to keep our angles small, and we also agree to work in radians, then we can cheat a bit. So if we go ahead and say we will let theta equal exactly small in radians, like I say, less than about 0.3 radians or so, that works. In that case, we can approximate sine theta with just plain theta itself. Now we can go ahead and put theta in for the sine theta here. So we can say that alpha is now approximately minus mgh over I theta, and oh hey, that does fit our prototype situation. If I go ahead and look at that, I get that this is a simple harmonic oscillator, and this would have to be 2 pi f squared. So we can go ahead and solve for that. We'll have 2 pi f squared equals mgh over I. So take the square root of both sides. 2 pi f is equal to mgh over I. Take the root, divide by 2 pi. We get the frequencies 1 over 2 pi root mgh over I. So again here, this is with the constraint that our angles are small. If they get to be more than about 0.3 of a radian or so, this approximation doesn't work anymore. But as long as the angles are small, we're good. So let's just try a quick example of that. So let's say that the object we're thinking about is a meter stick. Let's try to figure out, and we go ahead and just hang the meter stick right at its end. And again, we'll agree to not, so say the length here is a meter. And we will agree to not swing this more than about 20 degrees. I'd like to find what the frequency of oscillation is. Well, first thing we have to do is locate the center of mass. Well, it's a meter stick. It's going to be halfway down the stick. So we can just say that our h is 1/2 meter. Now let's write out 0.5. There we go. Now, using the result that we had, we can say, all right, 2 pi, I'm sorry, we had that f was equal to 1 over 2 pi root mgh over I. In fact, actually with h, let's just go and call that L over 2, and they'll be even easier. Let's do that. All right, so let's go and see if we can take this any further. So 1 over 2 pi root mg. Now for h, I'll put in L over 2. Then the moment of inertia of a rod swinging about its end, if you go and look it up in the tables, is 1/3 ml squared. So conveniently, I had never provided you with the mass of the meter stick, so it's a good thing that canceled. We also get 1 power of L canceling. And if we rationalize everything, what are we going to get here? we're going to have to move the 3 up to the numerator, 2 down to the denominator. So it's going to be 1 over 2 pi times square root of 3g over 2l. All right, well, let's go and put that in. So so our frequency will be 1 over 2 pi times 3 times 9.8 newtons per kilogram, which no one knows is going to immediately replace it with meters per second squared, over 2 times 1 meter. All right, so check in the units. When I cancel the meters, I leave behind a 1 over second squared. I'll be taking the square root of 1 over second squared, that's 1 over seconds, which is hertz, which is exactly what I want for my unit of frequency here. So we can go ahead and work that out as well. We will have, let's see, we'll take 3 and times that by 9.8, divide that by 2. We'll go ahead and take the square root. We'll divide that by 2 and by pi. And we get that a meter stick oscillates at 0.61, right? Yeah, 0.61 hertz. Or if you prefer to think about its period, we remember that the period is 1 over the frequency, or vice versa. So that would be 1 over 0.61 hertz. That'll give me a period of oscillation of about 1.6 seconds. So if you have a meter stick available, you just dangle it loosely by the end, by your finger. Start counting your Mississippis, and you should see that a complete oscillation there and back will take you a little less than 2 Mississippi. Alrighty. Now it seems like the long way around, but now that we've solved for this physical pendulum, that finally lets us get to the simple pendulum. And this is because the simple pendulum is an application of the physical pendulum. Simple pendulum is just a mass at the end of a lightweight string or thread or something like that. Just tie a string around a ball or something like that, and you're good to go. So here, what we'll do is we'll just treat the string as if it were massless. Again, we will pinky swear that we will never swing this past where small angles won't work for us. So we're going to keep the angle to less than about 0.3 radians or so. And we just have this mass at the end of a massless string. So we'll just say the distance from the attachment point to the mass is L. That will be also equal to the location of our center of gravity here. So I can go ahead, do the same thing as before, and say we found before that the frequency was 1 over 2 pi root mgh over L. Well, in this case here, 1 over 2 pi root mg, well, h just plain is L, and actually not over L, over I, my bad there. And the moment of inertia will just be ml squared. The tables will usually say mr squared, but again, that's just the distance from here to there. So m's cancel, l's cancel, and you are left with the frequency being 1 over 2 pi root g over L. Okay. So a version, so as an example of this, let's say that you were to take a pendulum that was, oh, let's say the string was 2 meters long, and you're to swing it on Earth. Now you got a friend who's in that newly established lunar colony that exists only in my dreams, unfortunately. And you want to be so that their pendulum swings at the same frequency as yours. How long should their pendulum be? So let's say here you are on the Earth. Oh, we gotta make sure you're on the Earth. There we go. So the length of this pendulum bob on Earth is 2 meters. And when you build another one on the moon, I'm giving the storage shorter. We want to know how long should it be on the moon. And we can remember that the gravitational field strength on the moon is pretty darn close to 1/6 that on the Earth. Oh, we gotta have someone, we have to draw in your friend. That would be really sad if we didn't draw in your friend. Okay, I tried really hard to draw a spacesuit there. Didn't work out so good. All right, so if we want them to keep the same rate, Earth and Moon, we can just demand that the frequencies be equal, right? So let's just demand that the frequency on the Moon be equal to the frequency on the Earth. So we just found that the frequency is 1/2 pi root g over L. So here this would be g of the moon, L of the moon. And that had to equal 1/2 pi. Same deal on Earth, g for the Earth, and the length of the pendulum on the Earth. Alrighty. Well, oops, we can cancel 1/2 pi's, and we can square both sides. So that will give me g moon over L moon equals g Earth over L Earth. So we can go ahead and rearrange this to solve for L moon. So the length on the moon will be, let's see, yep, g moon over g Earth times the length on the Earth. But we said that g moon was about 1/6 that of the Earth. So we can cancel those bits. To get that, it should be 1/6 the length on the Earth. Well, we said that that was 2 meters before. So your friend's pendulum should be 1/3